Today I wanted to go through a bit how to do but quite simple Verilog simulation together with Ngspice. So these type of mixed signal simulations is sometimes necessary to combine the wonderful world of digital with the amazing world of analog. So let's dive in. So first of all, if you don't know much about spice simulation or things like that, I think it makes sense to go through a few details. So when it comes to digital simulation, the reason we can do like ultra big complex processors and GPUs and the fantastic things that we've been seeing over the past 50 years is because we've been able to simplify simulation of complex system through what we call digital simulations. So these are simulations where you really only care about two values, 1 or 0. Well, actually, it's slightly more. You have X's and you have high impedance and so on, but let's assume it's 1, 0. And maybe the most importantly, that the execution of things that happen goes at a known, not necessarily known cadence, but in order. So whenever a AND gate, for example, gets an updated input, it will schedule an event in the future where the updated output is made. It doesn't, the digital simulations tools don't really do complex mathematics in order to compute what the output should be. It has very, very simple rules. For example, let's take an inverter. If the input is 1 now and was 1 in the past, well, then the output will be 0. If the input has changed to changed to 0, then in the future, the output should change to 1. And the way digital simulations schedule these is, let's say, okay, in the future, at some certain time point, it will change to 1. And that means that the system is causal. It's quite easy to write, well, easy. It's trivial to write a digital simulator that sort of runs through everything that happens at the current now and then steps into the future and does the next thing. So with this simplification of the real world, it is possible to simulate very complex systems. There are many commercial digital simulators, but there are also a couple of open source ones. You have iVerilog, and I guess Verilog or iVerilog is the one you would use. I think the iVerilog is actually the compiler, and the VPP is the somehow the stuff that runs it. You also have Verilator, which is slightly different. I just included for fun. I wouldn't necessarily recommend it. During my PhD, I wrote a digital simulator in C# because, well, I programmed a lot in C# at that time, so why not? It was fun to do. Anyway, when we write digital code or digital hardware description languages like VHDL or preferably Verilog or SystemVerilog, they are made in order to communicate how to generate hardware. So when we write complex chips, we do it in a description language like this, like Verilog. So this is a very simple module that takes in a clock, it takes in a reset, and it outputs a B that is 5 bits wide. And this module is really simple. On a pulse edge of the clock, it checks the reset signal, and if it's supposed to reset, then it'll reset internally. And then if it's in reset state, then the B is 0. And if it's not in reset state, well, the output increments. So in these type of SystemVerilog languages, it is comfortable and nice and a warm fuzzy feeling to write these type of functions. It's easy. In analog simulation, what I'm showing you right now to make a counter that runs fast and, well, in pure spice with sources and with voltage controlled sources and things like that, it actually is quite hard. So, but our circuit that we want to simulate, the analog circuit, that has to be simulated in an analog simulator because it can't use a digital simulator. And one of the reasons for that is we don't know what the time step should be, for example, because the speed of an analog circuit depends on the components, the resistances, the capacitance, and transistors, and it can be non-linear. So what you actually have to do in a SPICE simulation is to set up the expression, the mathematical expression for the relationship between all the voltages, all the nodes in the circuit, and all the currents between nodes in the circuit, which will then be proportional to a conductance matrix. So between all the voltages and all the currents between all the nodes that have components, there will be a conductance. So for example, if there between node V1 and V2 was a resistor, I guess V1 and V2 would be the conductance G12. So if that was a resistor, then we would have a constant here, if it was a constant resistor. If it was a transistor, well, then the conductance would actually depend on a different voltage. So this is sort of a complex set of partial differential equations that is solved in the engine that is the SPICE. SPICE mathematical insights. Here they will use sort of integration methods or numerical time evolution prediction of these sets of partial differential equations. And we're not going to go into that because I don't understand it yet. Well, yet. I don't know if I'll ever understand it. I'll probably never go deep on how to do SPICE simulation inside the Ngspice, for example. Because you can buy them. You can buy the gold standard, which is Spectre. Or you can get the open source one, or free ones. Or you can get the open source Ngspice, and that's what we'll be using today. Okay, so when we're combining a digital simulator with an analog simulator, it's not trivial. You can't take the RTL code or the Verilog code and run it directly in the analog simulator. It's not made for that. It doesn't know how to set up the partial differential equations for the Verilog code. And the same for the vice versa. You can't take the partial differential equations and easily port them into a digital simulator. So what you need is both. You need both simulators, but they need to work together. So the signals from the digital simulator need to be translated into analog signals. So this would be the B's, and this would be the output from the counter we looked at earlier. That has to come into the analog simulator, and then there may be feedback from the analog circuit back into the digital. For example, there would be a comparator. I don't have that in this example, but you can imagine feedback back into the digital simulator. And then there would be some sort of master event time step control. Somebody keeps the cadence between these two simulators. So for example, the analog simulator would compute a few nanoseconds and picoseconds or something like that in the future. And when it gets to a point where the digital simulator has an event, well, then the digital simulator takes all the inputs from the analog and then computes what's going to happen to the digital outputs. And then the analog simulator, well, in the next sort of iteration of its partial differential equations, it will compute the time evolution and how this behaves. So, complicated, difficult, tricky, but not necessarily tricky to run it. So what I've done is try to make a relatively simple example of how to do these type of co-simulations of an RTL and a analog block. So you'll find a tutorial like this. I'll go through a bit of this in detail, so don't worry. And you'll find the schematics that describe what it is and how to get that tutorial. I'll put the links in the description below. And there is also a repository on GitHub where you can clone the whole thing and you can test it out for yourself. Now, using this repository actually assumes that you have used the tutorial I made before. So maybe I need to put that into the notes also. So there's a previous video on that. I'll try to remember to, let me just update the slide decks here so I'll remember to put it in. Let's see, where's the demo? There we go. Assumes knowledge of there we go. Okay. No, I don't want the space there. Okay. So let's get to the, well, let's go through the steps first. And then at the end, I'll show how it works. So this is our analog block. It is a current mirror. We get a bias current in here. And this is the diode connector transistor. We have a few output currents. And then this section is a digital to analog converter. And actually, maybe it's a bit small, so let's open the schematic. So here I have that Git repo. And we can open up the schematic. So this is the top level. We're going to look inside the DAC. And let's make it bigger. Yeah, so this is the digital to analog converter. It basically has the same NMOS current mirror outputs, but we can see that here the number of units has changed. So here we have 1, 2, 4, 8. And then on the first couple of units, it actually is 2 transistors in series. So that it's not entirely half, but roughly half. And then for each of the scaling, the binary scaled transistors, we have a switch that is controlled by a digital signal. So this is the one we kind of want to sweep and then see how the output current changes. Okay, so in order to, well, we need our Verilog code. We looked at that before. So that actually gives us this ramp on the B output. So that we want to put into our analog simulator. Now, the first thing we need to do is actually to compile the Ngspice. And, oh, sorry, the RTL. And that's done using a program called Verilator. So you actually need Verilator on your design. So let's go to the simulation directory. I think I'll just run the demo while I'm speaking, and then we'll look at the end what I've forgotten to do. Note that in everything I do, I will, so let's go to the simulation, that one. I will always have a makefile that where I've written down the commands that I need to execute. And actually, maybe let's make it even bigger. Let's see, maybe 20. Okay, hopefully you can see that. Yeah. Okay, so the first thing we need to do is to compile the Verilog. Ah, crap. That one. Okay, so here we're using, or Ngspice is using Verilator in order to compile the Verilog. So it'll take the digital as the input. Digital was the one we looked at. And it's important that you have to use, I think it's Ngspice 43 and up. In the older Ngspice versions, it will not work. Or maybe it was introduced in 42. I don't know. Just use the latest one. If you don't have it, then you have to compile it. So what this will do is it will make a object directory. Actually, let's open that. So Verilator translates your digital design into C code actually. So I think if we look at, for example, inputs, we will recognize we have the clock and the reset. We have the outputs. where there we have the 8-bit bus, or it's using 8-bit bus internally, but it's a 4-bit bus, 5-bit bus. That is the B output. And I guess there will be some Verilog code here. And this C code is actually what Ngspice does. Ngspice runs to call evaluate a step, for example. So I assume in here somehow it has the code in order to figure out, is there supposed to happen something at this time step? I haven't gone into the details of this code. What comes out is what's called a shared objects file, the SO file, and that's the one we have to include into our Ngspice simulation. Now, in order to do that, we have to tell Ngspice a lot of stuff. Now, I'm quite lazy. I detest doing the same things over and over again, which means that I have written a Perl script that you can use in order to generate the Spice file that you need. Because in order to get this SO file, this object file, into Ngspice, you have to tell Ngspice a lot of things. For example, you have to say edit, and then you have to give all the inputs, and then you have to give all the outputs in the correct order, that is in the Verilog file. And then null here, that's because currently I don't think it supports in-out. And then you have to specify it's using a model that's called d_cosim, and that has to put in the SO file. And I will also change the delay. I guess this is from input to output to 10 picoseconds, so it actually has some delay. In addition to that, it turns out that for all the inputs and outputs, especially the outputs, for Ngspice to actually compute those values, it needs to have something connected to it, apparently. So I connect a gigaohm resistor from the output to ground. This would add some leakage current, so if you're operating your circuit in nanoamps, you have to change this value yourself. And then, since it's a pain to look at the digital output signals in my waveform viewer, I combine them into a bus. So this dec_b is using this is an E source in order to compute what the decimal value of the bus is. So you take 16 times the biggest, or the MSB, and then 1 times the smallest one, and I divide the whole thing by 1,000, so I get, I don't get kilovolts and stuff in my Spice simulation. Usually that doesn't matter, but it could with regards to the absolute tolerance. And then I save. So this file is generated by this Perl script that I have. Now, we could look at that Perl script if we wanted to. So that's in the technology, scripts, gen sveinst. And what does it do? Well, it opens a file. It tries to find the module name and tries to find the ports. That's what it's doing here. So it removes the comments from the ports, removes new lines from the ports, and then based on the ports, it's, lists, just trailing spaces, and it tries to split up, so it gets the port names, and whether it's an input or an output, puts those into a dictionary, and then just collects the data here. So this would be the name, whether this is a bus, so it has a start and a stop and a direction. And then based on that, it will, for each of the inputs, it generates the resistors, and for each of the outputs, it generate resistors, and for each of the outputs, it will make those observable buses. So all in all, when we then run this command, so here, if you're using your own stuff, you would need to change it to your RTL code and so on. But that gives you this sveinst file. Let's open that in Emacs. And that has the same code as we looked at before. So that means I have a instance file, this sveinstance file, that I can just include in my testbench. Okay, so once I have that, then in my testbench, let's go through that a bit. So that's tran.spy. Okay, so here I include my Spice circuit. Just a few options for the rise fall time of my clock and reset, the period and so on. Set up my supplies. Actually, it is a bit small. Let's make it even bigger. I want you to be able to see it. Yeah, that's better. Set up the clock, set up reset, and here I have my device on the test. So let's open that, just have a look. So this is just also a generated file that gives me the instance of the XGAM schematic. So I use this kind of thing because I don't want to write this manually, because if I change the port in XGAM, or if I remove a port and I forget to update the instance, then my simulation doesn't work and so on. And then we have the sveinst. Now, I've used different names in my xtut compared to my sveinst. So my Verilog doesn't have the same names, because that will always be B.4 for the bus. So I need to translate those. So I just use DC voltage sources to translate those. And then I have my bias current, 100 nanoamps. Now, this next section, this is just an RC filter on the DAC output voltage, because when the binary DAC switches, there will be charge injection and glitches and blah, blah, blah. And I just don't want to see that in my simulator. So this is a small cheat. And then we have the other bias currents. I set the voltage so I'm able to measure it. So the way to measure currents in a Ngspice is you need a voltage source, I think. And then I save a bunch of stuff. And then last but not least, in order to get the levels to what I'm using in my design, I'm using this preset auto bridge thing. I found that somewhere, I don't remember where, but this sets the output voltage of the digital drive levels. So that means you can adapt it to different type of analog circuits, and then run it for 32 microseconds. So let's run that simulation, and also let's make this even bigger. Make typical. Here, if you don't, well, yeah, so make typical actually generates the digital, it generates the analog, so Spice file, and then runs the simulation. Actually, now it doesn't run because I haven't changed any files. It also has this hash function that doesn't rerun simulation if it's not necessary. But that actually, let's no SHA. Let's force it to run. Oh, that didn't work. Oh, wasn't that C up? Just a second. Oh, I don't have that. Okay. Let's do like that to get the N. We want no SHA to force the simulation to run. Okay, so now Ngspice will open the test bench, it will do the simulation, and let's see if it says anything. Oh, what happened here? It didn't find a digso. Okay. Did I stop it before it generated it? Probably. Yeah. Let's run it again. Okay, now we can see it running. Yep, so it does. Yeah, it does multiple simulations, and now I discover the wrong directory. Oh, wow. Doesn't really matter, it's the same thing here. Make typical. Okay, so now let's run through the simulation, and we can see that the maximum DAC current was 1.6 microamps, and the minimum was, what is that? 50 nanoamps. Okay, so let's look at the waveforms. And we were doing that simulation. So that's in the raw file. Here I'm using my own CIC sim wave, just because I find it easier to use than Ngspice. It's not perfect, so if you want to add feature to it, be my guest. It's missing a print feature. So here we can see the B output, or actually it's not the B output, it's this bus thing that I made. And let's add another axis to look at the current from the DAC. And here we can see the current from the DAC. So it starts out at, let's see. I just realized something. This doesn't have the units. See, it's not a perfect simulator. It's not a perfect waveform mirror. But we can see that the current starts here at 2 microamps. Oh, right. So the current goes down because it's negative. No. Why? Oh, this is the DAC value. That's why it looks weird. We want the current. That one. Okay. Yay. Okay, perfect. So it starts out here at 40 nanoamps. Or minus 14 nanoamps. And as we increase the B value, we can see that the current in the output changes. So now we have a very easy way of changing the Bs, or maybe having a feedback loop with a comparator, or whatever you want to do. You have a way to write code easily in Verilog and then run a simulation on it. Okay, that's pretty much what I wanted to go through today. So I would encourage you to have a look at the examples, try your own, try to make it, try to use the scripts if you want to. Note that the scripts that I'm using to translate stuff, that's in this technology folder in these packages, and that's links from another repository. But that's all defined in this config file. Watch the Skywater tutorial and you'll figure out how these folders and repositories work. So good luck. Maybe one note at the end. If you go into the documentation here, or indeed the repository, you will see that the simulation is failing. So here I'm trying to run the simulation on the GitHub servers, but turns out that the Docker image I'm using doesn't have Verilator yet. So that's why it doesn't work. I need to install that in the Docker image. I'll do that someday, but not today. Maybe today. I don't know. Let's see. Have a fabulous, fantastic day. Bye-bye.